Today we're going to look at section 1.3, and in this section we're going to focus on estimation. So in the last few sections we've talked about our problem solving strategies and our inductive and deductive reasoning, and this is the last section in chapter 1, and we round that out with estimation. Sometimes we're going to be in situations where it's going to be very beneficial if we can utilize our mental math skills and kind of estimate, for instance, how much we would have to pay after leaving a specific tip, or how much we would need to pay if something was on sale at a % of a discount. So we're going to look at just some estimation in this section today. So if we are working on estimation, we have a couple of different strategies we can utilize as we go through these problems. The first is looking at rounding to make estimates. So when we are rounding, we do want to make sure we remember a couple things. When we're rounding, we look at the digit to the right of the digit that's being rounded. And if the digit to the right is 5 or greater, we round up. Otherwise, we round down. So with that, we do want to make sure we spend some time reviewing our place value chart, remembering from our decimal point, anything to the right behind the decimal point, we've got our tenths, our hundredths, and our thousandths. And then anything to the left of that decimal point, we started our ones, tens, hundreds, thousands, 10,000s, 100,000s, and millions. So we have that whole part, and then we have our decimal part. So we start off with just a little bit of review with those rounding skills. So we went around using decimal notation to the nearest place value that's going to be indicated. So with part A, we are rounding 2,643.7 to the nearest 100. So when we look at the hundreds place, there is that 6 that's sitting there. So we are looking at the digit right next to it, which is the 4. And since 4 is less than 5, we are going to round down to a value of 2,600. Part B, we're rounding to the nearest tenth. So tenth is behind our decimal, is the 1. And if we look at the digit right beside that, we have a 6. So 6 is bigger than 5, so we're going to round up. And so when we round up, we end up with 7,327.2. Part C, we're rounding to the nearest 1. So our 1's position is sitting right here in front of the decimal. The digit right to the right is the first digit behind the decimal. So this is less than 5, so we round down. So that is going to give us 1,200. Part D is looking at rounding to the nearest hundredth. So the hundredth is behind the decimal. It's that second position. So we look at what's sitting to the right of it, and we have our 4. And so 4 is smaller than 5, so we are going to look at rounding down. So when we round down, we get 0.20. And the last one we have right here is rounding to the nearest thousandth. So again, that is behind the decimal. That is the third position behind the decimal. So when we look at the digit to the right of that, we have that 6, which is bigger than 5. So we are going to round up. And so that will give us 35.193. So as we said before, we want to make sure we're spending some time with those different place values and just make sure we're comfortable with them so that when we have those situations that require those rounding skills, we can focus on the correct place value. So next we're going to look at some examples where we're using those rounding skills to calculate some estimates. So with part A, we have our 4 numbers that are being added together. And in this particular example, we're going to look at rounding each of them to the nearest 10 first before we actually go ahead and get that estimate. So if we look at rounding to the nearest 10 with each of these, we have 17, so the 7 forces us to round up to 20, plus 27, again the 7 forces us to round up to 30, plus 10, so the 0 forces us to round down, plus 87, so again the 7 forces us to round up to 90, and so now we can add those values together to get our estimate of 150. With the next example, part B, we're also going to look at rounding to the nearest 10. So again, if we think about the nearest 10, the 10th place is 0. So looking at the digit beside it is 7. So we're going to round up to 110 minus, again, thinking about that 10th place, we're going to round up to 70. So 110 minus 70 is going to give us 40. Part C, we're going to round the first value to the nearest 1,000. So looking at what comes behind it, in the hundreds place is a 0, so that's going to stay at 1,000. And we're going to multiply it by, with our second number, we're going to round it to the nearest 1. So to the nearest 1's place, so the digit to the right of that is 8, rounding that up to 15. And when we multiply, we're going to get 15,000. Part D, we've got some division, so we're going to round the first one to the nearest 100. So when we look to the right, that 6 forces us to round up to 2,100. Divided by, with the second one, we're going to round to the nearest 10 on this one. So looking at the 2 that's sitting beside it, that's going to force us to round down to 70. And so then when we do 2,100 divided by 70, we do get 30. Part E, we're going to round the first one to the nearest 1,000th. So that's behind the decimal right here. So the 8 will force us to round up. So it's going to be 0.001 times. With the second digit, we're going to round to the nearest 1,000. So there's a 0 to the right of that, which will round down to 4,000. So if we do 0.001 times 4,000, we get a value of 4. And with part F, we have that percentage, but we're not going to worry about the percent sign for now. We're going to round that to the nearest 10. So the 8 forces us to round up to 20%. Times, with the second value, we're going to round to the nearest 100. So the 8 sitting to the right forces us to round up to 700. And so then we're going to multiply. So with this one, when we're thinking about kind of those mental math skills, we could think of if we started with 10%. Well, what is 10% of 700? That would be 70. So if we think about 20%, we're just doubling that. So 20% times 700 is going to be 140. Okay, so that's just a little bit of review with our rounding skills. So the first example that we have coming out of the textbook looks at estimating a grocery bill. So you stop at the supermarket on your way home. You have a few items on your list. You also really want to buy a half gallon of ice cream, but you only have $20 in your wallet. So the ice cream is going to cost $3.59. You don't want to go to checkout and not have enough money. So we're going to use our rounding skills to the nearest 10 cents, so that would be to the nearest 10th place, to estimate the total cost of the purchases. So looking at our 10th place in all of these, and then looking at what's sitting on the right to make that distinction about if we're rounding up or rounding down. So with cereal, rounded to the nearest 10 is going to be 4.30. Our milk to the nearest 10 is going to be 2.40. Bread to the nearest 10th is going to be 1.90. Lunch meat to the nearest 10th is going to be 3.40. Pickles to the nearest 10th is going to be 2.40. Dishwashing liquid to the nearest 10th is going to be 2.90. So if we combine those values for our total estimate, we find it's going to be $17.30. And that's estimating the total cost. So that total cost, that estimate, is $17.30. So then part B wants us to make a decision about if we should get the ice cream or not based on the estimate we have. So if the estimate for all of these items is already $17.30 and we only have $20, if we look at the ice cream, if we estimate that to the nearest 10 cents as well, that's $3.60. But that would put us over the $20 limit. So the ice cream is too expensive. And so down below, they give us some good advice that reminds us that we don't necessarily need a calculator to add those estimated prices. We can look at combining them 2 items at a time and then continuing to just add on the next item to that previous total until we get to the $17.30. And so that's important to think about because we may not always have a calculator on us, or we may not feel like trying to pull out our phone and open the calculator app, especially if our battery is pretty low and we don't want it to die on us. So it's important that we get comfortable with those little mental math skills so that we can quickly and effectively use those when we're in that type of situation. Another approach we have is what we call using compatible numbers. So when we're using compatible numbers, it's not so much focused on rounding. We're choosing convenient numbers that are easier to work with and then substituting those in to be able to perform the indicated operation. And so we look at an example of that if we think about going to Buffalo Wild Wings and trying to figure out how much we want to tip. So we are told that our bill at Buffalo Wild Wings is $37.86. We want to use compatible numbers to calculate a 15% tip. So like we said, with compatible numbers, we're choosing a convenient number that's relatively close to the value we started with. So if we focus on that 86, then a convenient compatible number that's relatively close to this would be if we went up above this to $40. And we can keep that tip at the 15%. So if we are trying to calculate our tip, we would look at taking that $40 and we could split that 15% tip into 10% and 5%. So then we could perform those calculations and think about, well, what's 40 times 10%? And what's 40 times 5%. And then we would just combine those two values. So if we take 40 and multiply it by 10%, we're going to get 4. 40 times 5% is going to be 2. So then if we combine those, 4 plus 2 is going to equal 6. So this tells us that the tip is roughly $6. And we know in this situation, because the compatible number we chose was bigger than our actual cost, this tip of $6 is actually a little bit more than what a 15% tip would be. So another piece of advice is that when we are making the estimate, it's good to think about if it's going to be reasonable. So we should have an idea as to whether that estimate is too big or too small. So like we said here, the $6 tip is a little bit more than 15%, which does seem quite reasonable for a $40 meal. So the next thing that we look at is a little bit of review with being able to convert between fractions, decimals, and percents, because we are going to be working with all of them. So by definition, percents are the result of expressing numbers as part of 100. The word percent means per 100. So we notice right here they give us whatever that number is with the percent sign, and then they show us that equals, in fraction form, that number over 100. So 100% is equal to 1, and if you have a percent that's larger than 100%, that number is bigger than 1. So with part A, we want to change 35% into a fraction. So if we want to convert that into a fraction, we can set it up using that relationship they give us. So it would be 35 over 100. From here, once we have a fraction, we do want it in that reduced, in that most simplified form. So then we focus on, is there a number I can divide both the top and bottom by to make this smaller? And in this case, we notice 35 and 100 are both able to be divided by 5. They're both divisible by 5, so we go ahead and divide, and we get our simplified fraction of 7 over 20. And we cannot simplify those anymore because 7 is a prime number. The only factors are 1 and 7, and 20 is not divisible by 7. Part B wants us to look at changing 5% into a decimal. So again, we have 5 over 100. And so if we think about the fact that this is divisible by 5 again, that would give us a reduced fraction of 1 over 20. However, this problem wants it as a decimal. So if we go ahead and we calculate 1 divided by 20, we're going to get a decimal value of 0.05. Now, when we are working with percentages, we are able to, if we remember, kind of like a little memory device. So to convert from a percent to a decimal, there are two things we want to do. Number one, locate the decimal point in the percent. So what I mean by that is, if we take this example, we look at 5%. There's no decimal that we can clearly see anywhere with our own two eyes, but it's understood that the decimal point is sitting right behind the 5. So we identify that. So we have 5 and our decimal point is right behind it. Once we do that, then we move the decimal 2 places to the left. So in this case, we've got our decimal. We're moving it 1 position to the left, and we're moving it another position to the left. So our decimal is going to end up right here. Now we notice in doing that, we do have a little gap right there as we moved it. So in that little position, that's a gap. We always fill in a gap with a 0. So that shows us 5% is equal to 0.05. Okay. So we can always think about this if we're converting from a percentage into a decimal. So now we're going to look at a few examples using those techniques of rounding or compatible numbers. And so we're going to estimate each of the following answers. We're going to explain how we made the estimate, and if possible, state whether our estimate is larger or smaller than the exact value. Part A says Julia is purchasing 18 packs of pencils at 94 cents per pack. What is her bill? So if we're using estimation for this, we can look at taking the 20 packs that she purchased, and we could round 18 packs to the nearest 10, which in this case would be 20 packs. We could also look at the 94 cents per pack and round that to the nearest ones place, which would put us at $1, because the 9 that's sitting beside that would force us to round up, just like the 8 sitting beside the 1 would force us to round up. So then we can take both of those values and set them up with multiplication. So we have 20 times $1 is going to be $20. So that would be our estimate. However, since we rounded both of those values up, this estimate is going to be larger than the exact answer. Part B, at a gas station on the turnpike, Raphael spent $57.60 for 14.8 gallons of gas. Estimate the price he paid per gallon. So if we're looking at how much he spent $57.60. So if we want to look at how much he spent there, we could round that to $60. If we round to the nearest tens again, that 7 will force us to round up. We also know that he paid for 14.8 gallons of gas. So we could round that to the nearest ones. So if we do that, looking at what's sitting beside the 1, so we got 14.8. So focusing on the 8, that forces us to round up to 15. And so then if we're trying to figure out how much he paid per gallon, this time we're not going to be multiplying, we're going to be dividing. So we set this up as $60 divided by 15 gallons means he paid $4 per gallon. And so again, in this case, we rounded both of these up. So this is going to be larger than the actual value. It's going to be an overestimate. Part C says Ted, Lily, and Marshall share an apartment. Their total utilities bill for last month was $76.38. What is each person's share of the bill? So we have the total, which is $76.38. So we could use compatible numbers here. And if we're choosing a convenient number close to $76.38, we could choose $75. That's a pretty convenient number, especially given the fact that we're looking at Ted, Lily, and Marshall, so that is 3 people. And if our goal is to figure out each person's share of the bill, we're taking the $75, dividing it by the 3 individuals, and we're going to get $25. Now, in this case, since we rounded down and we chose a compatible number that's smaller, this amount is going to be smaller than the actual amount. Part D, Sandra bought a new computer for $1,389. If the sales tax is 6%, what is her total bill? So again, we can look at using our compatible numbers. So the computer is $1,389. Again, a compatible number, we could use something relatively close to that. We could look at if we did $1,500. And the sales tax is 6%, so we could keep that at 6%. So we'd have 1,500 times 6% because we are looking at the sales tax. So when we calculate those together, we end up with $90. And so then if we want the total bill, we're going to have to take the original cost that we estimated, $1,500, and add it to that tax. Add it to that tax of $90. So that would give us $1,590. And this, again, since we used a compatible number that was bigger, this is going to be larger than our actual value. Part E says an elevator has a capacity of 2,300 pounds. Alicia and her 5th grade class of 21 students want to crowd into the elevator. Do you think it is safe? And explain. So if we use compatible numbers again, then we can look at the fact that the capacity is 2,300 pounds. So a relatively close compatible number would be 2,500 pounds. And it's Alicia and her 5th grade class of 21 students. So we could estimate kind of close to that would be 20. So we could divide this by 20. And so that gives us 125. So that means we would have 125 pounds per individual. But considering we increased the weight capacity and lowered the number of individuals, okay, if we think about, is this safe for all of them to crowd on there? Well, these are 5th graders, so no. The combined weight may exceed the weight limit. So our last example of this type is part F. Ben bought a new car for $19,880 and paid a 2.5% sales tax. he can deduct this amount on his federal income tax return. If he is in the 21% bracket, how much will his deduction save him? So this problem has multiple parts to it. The first thing we need to do is look at how much is he going to pay in sales tax. So we are using compatible numbers again. And so we know that Ben's new car is $19,880. So we can approximate and say that's about $20,000. And he paid the 2.5% sales tax. So we're going to multiply by the 2.5% sales tax. And so when we multiply, that's going to be $500. And so now we want to look at saying the fact that he can deduct this on his income tax. He's in the 21% bracket. So if we're trying to figure out how much this will save him, we have to take the amount he paid in sales tax and multiply it by that percentage of that bracket. So we can, again, use compatible numbers. That's about 20%. So we're going to multiply it by 20% to get a total of $100. So it will save him $100. Next, we're going to look at other ways we can estimate information. So we're going to start by looking at, if we have a graphical representation of some data, how we can make estimations using those graphs that we're given. So the next example we have says that according to the U.S. Census Bureau, by the year 2050, the population of the United States will be 419,854,000. Use the graph to estimate the number of Hispanics who will be living in the United States in 2050. So we're going to do this with compatible numbers. So the first thing we're going to look at is the population of the U.S. at that time. So if we look at the population of the U.S. in the year 2050, they're saying it's going to be 419,854,000. So we can estimate that to about roughly 400 million. We are also focused on the number of Hispanics who are going to be living in the U.S. at that time. So if we look at the pie chart we have right here, we can see that Hispanic is 24.4%. So we can estimate that to 25% and use that in this calculation. So we're doing our 400 million times 25%. And that is going to be approximately 100 million. So by the year 2050, there will be roughly 100 million Hispanics living in the United States. Okay. The next part, there is another example that's very similar for you to try on your own. And so the graph in the next example is going to be based on a report from the Council of Contemporary Families, all at the University of Texas. regarding gender revolution in the way housework done as families has changed over the last 50 years. It's a good example that shows us that representing data in a rather careless way puts the people that are analyzing and looking at the graphs in a position to draw some false conclusions because of how careless the graphs were constructed. So we want to take a quick look at both of these graphs, and both of these, just kind of at a glance, seem to suggest that men are now doing more housework than women on a daily basis. So the question they give us as our thinking point is, what is misleading about the way we're presenting this information? So if we really analyze these two graphs, we notice on the bottom axis, on that horizontal axis, we've got years, 1960, 1970, 1980, so on. Those are consistent. However, if we look at that vertical axis on the side, the y-axis, if we compare for women and we compare for men, with women, look at how those numbers are distributed on that axis compared to how those numbers are distributed on that axis for the men. So we can see that there is not consistency in the way that vertical axis is being represented. There is a lot of inconsistency there. And so that does lead to that false conclusion that men are doing more daily housework than women are because of the way the graph is represented. So we could say the vertical axes are not consistently represented, and so that is what's causing the graphs and the information to be misleading. If we were to take those and kind of put them on the same graph and rescale so that we have the same representation on that vertical axis here, we can see that there is definitely been a decline in the amount of housework that women do on the daily basis, and a slight incline for the amount that men do, but it is still fairly obvious with this representation of the data that women are still doing more housework on a daily basis than men are. So it's important to just keep those things in mind when we're analyzing a graph or a visual representation of data. So we're going to look at using some graphs with our estimation. So we have a graph that shows the gender pay gap in yearly salary between men and women according to education in 2019. So we have two parts here. Part A says estimate how much more per year men with bachelor's degrees make than women with bachelor's degrees. So we are focused for part A on bachelor's degrees. And we notice with the key they give us, the blue is the bar for males and the red is the bar for females. So if we're just focused on bachelor's degrees and we are estimating, we're kind of estimating using the height of that bar. So with our men, our males, it looks like that would be approximately 65,000. And with our women, the red bar, that looks to be about 45,000. And so if we're thinking about how much more, we are wanting to find a difference. So we are wanting to subtract. So we said it looks like men are making about 65,000 and women, it looks like are making about 45,000. So we subtract those to get our estimate for the difference and find that that's going to be about a $20,000 difference. Part B says, on average, how much more do men college graduates make annually than men high school graduates? And actually, we're going to change this from college graduates to our bachelor degrees. So how much do men with bachelor degrees, how much more do they make annually than men with high school degrees? So again, our focus is on bachelor degrees, but this time we're also focused on high school. Now we are focused on men in both situations. So we said the bachelor's degree, men, it appears, make $65,000. And if we're thinking about how much more, we are going to be subtracting again in this example. And then if we look at the average for men that are high school graduates, we see that looks to be about $35,000. So after we subtract, we get our estimate to be about $30,000. So in using our estimation skills with graphs, we can also use them in other visual representations, such as estimations with distance on a map. So the next example tells us in the, that's supposed to say great, in the Great Alaska Challenge, boats will race from the starting point at Prudhoe Bay, which is point A right here, to the finish line at Kodiak, which is point F over here. Estimate the length of the race course. Assume that at any point, boats will take the shortest path. In this instance, we are going to have to rely on the key that they give us down here for analyzing and thinking about distance. So using the key, we can see, if we estimate that, the total length of the map is about 2 inches. Just by using those measurements to kind of estimate, okay, our inches. And so according to the scale shows us that 3/4 of an inch is going to equal 250 miles. And so if that's 3/4 of an inch, if we calculate and figure out, well, what is it for 1 inch? One inch is going to be the 250 miles times 4/3, which is 333 miles. And so using that, paired with the fact that the length of the map is about 2 inches, we just have to double the amount of miles. So the total length of the course is about 666 miles. Part B says if the boat, the Inuit, travels at 35 miles per hour, how long will it take for it to complete its course? So we have the length of the course is 666 miles. And we're also told in this case what the speed that boat is traveling at. So the boat is traveling at 35 miles per hour. So we just have to take the length of the course and divide it by the speed. So if we do that, we have the distance divided by the speed. That is going to give us approximately 19 hours. So that is about how long it's going to take the boat to complete this course. The next example we have is another pie chart showing a distribution of immigration into the US in a recent year. We want to use the graph to estimate the answers, and we're told the total number of immigrants was 705,361. So part A, how many people immigrated from Europe? So if we think about using the compatible numbers like we did before, we can look at Europe is 13.2% of the immigration. We also know the total number of immigrants. So if we use that with our compatible numbers, we can say the total number of immigrants is about 705,000. And those from Europe make up 13.2%. So multiplying the total number of immigrants with the percentage from Europe, we find that there are approximately 93,060 people that came from Europe. If 41,034 people immigrated from China, what percentage of the total, what percentage was that of the total number of immigrants? So in this case, we're looking at 41,034 people immigrated from China. So if we think about how many immigrated from China, we could round that to 40,000. And again, the total number of immigrants is 705,000. Now we are looking for the percentage, so we are actually going to divide. And we're dividing the number of people that came from China by the total number of immigrants. So that gives us 0.0567, which is approximately 5.7%. Next, we have estimating the size of a large number of objects. So let's say there's a political rally that's taking place, and the news media wants to report an estimate of the crowd. Because of the countless number of people in the crowd, they can't actually do a head count, so they just use this type of technique that we're going to look at in this example. And so this example is looking at if we have a certain number of M&Ms that we're trying to figure out. And we want to estimate the number of M&Ms that are visible in this figure. So looking at the figure, one of the things we notice is that the figure is divided into, if we count, 16 rectangles. And so if we focus on this rectangle right here, and we were to count how many M&Ms are in there, we could see there are about 10 M&Ms in the highlighted region. So keeping that in mind and using the fact that we have 16 regions, we can multiply 16 times 10 to get our estimate of about 160 M&Ms. A lot of times we have formulas that we have to use in geometry to help us with various figures, squares, triangles, circles, things like that. Sometimes we have a shape that we're given that doesn't really fit into one of those categories. And so we need to be a little creative in how we can find the area of a shape that's a little bit more irregular. So suppose that we have an environmental control officer spraying for the West Nile virus in a park, and they need an estimate of the area of the region shown. Assume that each square in the grid has dimensions of 1 unit by 1 unit and represents 1 acre. So one way that we can think about this is if we focus on kind of splitting this into 2 different regions or 2 different areas. And so we could look at all of the squares that are completely contained inside this figure. So if we look at all of the squares that are completely contained inside this figure, and from there we would look at how many of them are completely and entirely contained in this figure. And so if we look at this, we notice that there are we end up with 24 rectangles that are completely contained inside this figure. So our inside area is 24 acres. We can also look at how many of these are not completely contained in this figure. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And so with that, when we're thinking about how many are not completely contained, we found the inside area, but we also want to find the outside area. And so the outside area is looking at using the inside area, but also adding those other pieces. And so we are going to have areas that intersect. So our outside area is 55 acres. Like we said, looking at adding those inside areas and all of the pieces kind of sitting on the outside of this figure that we have kind of looked at indicating. So if we want to figure out the area that needs to be sprayed, we want to look at the total from the inside, the total from the outside, and then to get our estimate, we are going to take the average. So we're going to add the total number from the inside. We're going to add the outside, which is also still including the inner regions. And then we're going to divide that by 2 to take that into consideration. And so when we do that, we end up with an estimate of 39.5 acres. And so that would be our estimate of that irregular area.